So let's look into the last, and I think this is one of the most interesting part. What I'm going to discuss here is also going to be valid for audio, also for thermal imaging and so on and so forth, but I am going to discuss only vision and language. Yeah? So if you want to follow up, you can look at our papers and you can see audio language alignment and other stuff too. Okay, good. So now, more specifically, there are multiple methods. Yeah? There are now hundreds of methods doing that. I will pick up some of the methods which are more popular, and those are Flamingo, Lava, and Core VLM. Okay. So let's look at the Flamingo first. So when it comes to LLM, now LLM is trained typically on massive amount of data. So they are training on trillions of tokens and trillions of data points. Yeah. Essentially, some of the modern, for example, GPT-based models particularly, they are being trained on almost entire data which human has produced so far on internet. Yeah? Almost entire data. Similarly, Llama, which is coming from Meta, is also trained on large proportion, maybe 60% of the data which we have seen. So, yeah? So and this which is present on internet. So LLM have very core understanding of the semantics and the communication we humans are doing, and what those communications are about. They are about natural world. Yeah. So we use language to communicate what we see, what we feel, and so on and so forth. So we have major proportion of this. So let's not go into fantasy novels and stuff like that. A large proportion of the language which we are describing the events or the things which exist in the real world, and you can see them in terms of vision, or you can hear them in terms of audio. So these LLMs, the large language models, have that knowledge. And what we want to do is that don't disturb that knowledge, because the semantic space, in the semantic space, if you say cat or black and white cat, you will have an image of black and white cat. Yeah? I can ask you to draw an apple, a red apple, or a golden apple, or a green apple. You can do that. If I ask you a purple apple, you have never seen purple apple before, but you can draw it. Because you have semantic space, you can transform that into visual knowledge, yeah? If you are good in drawing. Okay. So the idea behind this visual language adopter is that you want to keep that knowledge intact, but you want to give the vision input to it as well, so that you can do interesting stuff. For example, you can do chatting, you can do grounding, you can do visual question answering, and all of these fancy stuff which we have seen at the beginning. Okay, good. So what we do here is that, so this is very, very simple and straightforward. We have image, we have image of a dog, image of a cat. We pass it through vision encoder, pre-trained vision encoder, and we freeze that vision encoder. And on the right, we have LLMs. And LLM is taken. So again, the training is done on the paired data. So you have image and you have corresponding text associated with it. Yeah. So for LLM, you are going to use LLM block. Everything which is in blue is frozen. Yeah. And everything which is in purple is going to be updated. Now I will go into different blocks which are here. So there is this perceiver sample, and this is gated cross attention. So I will look into that how you incorporate this knowledge from vision into your existing LLM without distorting what LLM has learned already. Yeah. So let's look into that. So let's look into perceiver. So it is coming from another paper. So they borrowed this component from there. So these are the bunch of images, and these images could be any. Yeah. In this case, it is representing samples from video. So uniformly sampled. Maybe this is one sample per second. So this is 1 second, 2 seconds, 3 seconds. So you take one sample. You take the vision encoder. You represent the data token for corresponding to vision encoder. You add the temporal position embedding. All the other position embedding should be added beforehand already anyway. And then you combine all of them into this XF. So far you are with me, yeah? Okay. Then you introduce latent token, randomly initialized latent token. You use that as queries, and you use this image token as K and V, and you do cross attention, nothing else. Yeah? Good? And we have studied cross attention in detail. And then you pass it through feed forward network. Now this only the latent queries which you have introduced goes to feed forward network. The output will be, in this case, 5 latent queries. So output will be 5 latent queries. And what these 5 latent queries are doing, they are going to represent the images which you are passing, which are in this case coming from video. Now if you pass 3 images, they will represent 3 images. If you pass 30 images, they will represent 30 images. If you pass low resolution images, they will represent low resolution images. If you pass high resolution images, they will represent high resolution images. At the end of the day, they are just summarizing the token using cross attention. Yeah. So that is all good. Yeah. So that is written here algorithmically. It is the same thing which I just said. Okay. Good. So that is my perceiver. Now I have a mechanism to take the vision, 1 input, 2 input, and summarize it and pass it to my LLM. So when I pass it through my LLM, I use this gated cross attention layer. Okay, so now what is that? So here is the gated cross attention layer. Okay. Okay, so what you have is, so this is the smaller block. So you can see that in the gated cross attention layer, you have this gated cross attention and you have LLM layer. And you have gated cross attention and you have LLM layer. And you do that for cross attention as well as cross attention MSA, multi-head self-attention component of LLM, as well as you do for feed-forward network. Both. You do it for both of them. Yeah. So now if I cover one of them, the other one is same. Yeah. Good. So this is now described here. So let's focus here. So you have input vision token, which is latent token coming from perceiver. Yeah. Good. And you have language token as well, which are represented here as Y. So the image token will become key and value, and this language token will become query, and you do cross attention. Nothing else. Yeah. So it's just cross attention. In the same way as you have done in perceiver. So it's simple cross attention, which we have been studying for a very long time. Okay. And then you pass the language token and do this skip connection as well. Good. So when the tokens are at this stage, so these are going to be language tokens. Let's say that you have 100 language token. Those 100 language token will represent, now are coded in terms of vision token, because key and value are coming from vision. So these language token here, so let's say that the vision token are coming from this this color. So the language tokens are coming from red. So at the output here, I will have blue token. Now that's it. They will go to feed forward network and so on and so forth. Yeah. So that this cross attention, one cross attention layer which they are introducing for the attention module is what is doing the trick. Okay, good. So once they introduce this skip connection back here, I will have tokens which are in terms of both language and vision. Yeah. So these tokens will be in terms of both language and vision, but they are already transformed into language space. If you think about it. Yeah. Okay. Good. And I do that. I pass them through feed forward network. So there is this thing. Okay. If I do that. If I don't do anything else, if I do that at the beginning of, because these layers which I am introducing, so there is this weights in this block, there are weight in feed forward block, and so on and so forth. Those weights are going to be initialized randomly. Yeah. If I start to do, if I don't take care, so what will happen is that the language input, the language branch here will start to get something which is not so good. Yeah. So which is noisy, it's problematic. So in order to tackle that, I pass it through a nonlinearity. Yeah, there are different ways to tackle this issue. For example, when we look at LoRa, we initialize it with 0, the weights, and that take care of it. When we are looking here, so you are introducing something which is called tangent hyperbolic gating. So it is very simple and straightforward. So what you have is your cross attention feature here. Yeah. And your cross attention feature, you multiply it with the tangent hyperbolic. And there is this parameter alpha tan hyperbolic. You initialize this alpha tan hyperbolic to 0. And tangent hyperbolic is a function which we have studied in detail, and it goes like that. So this is 0, 1, 2, 3, so on, -1, -2, so on. And it peak at 1, and it peak at -1. So we are initializing this at the beginning of your training with 0. So what this will give me? 0. So the output contribution from here and here at the beginning of the training will be 0, and that is fine. That will fix the problem. Yeah. So that is why we need tangent hyperbolic gating, not to deviate too much from the language space which we have. Okay. After doing that, now that this is complete. So what I want is basically next token prediction. That's it. Because my LLM is trained using next token prediction, I now have supplied the visual information, visual data. I want to keep the language model frozen. I want to keep the vision encoder frozen, and I want to only update receiver, and I want to only update this gated cross attention layer I had just introduced using autoregressive next token prediction loss. Nothing else. Good. Once you do that, you can choose to, once these purple blocks are trained, you can from scratch. So you can choose to fine tune the whole thing as well. You can choose to fine tune the LLM as well. Okay. So this is one of the first way to do this, and this gives you very decent results. As you can see that they are showing it. So you can do input prompt. You can give this image and corresponding text. You can give this image and corresponding text, and you can ask the model by supplying this third image, and you can say this is, and it will generate a flamingo. They were found in Caribbean, and so on and so forth. So this is the prompting. Simple. You can say that this is, so now this is actually text reading from the OCR, essentially, optical character recognition. So you are giving this underground congress and whatever this is, and it will tell you the corresponding answer. Okay, and they showed that when they are doing this thing for few shot learning, they are outperforming all of the existing few shot learning methods for this. So you can, this was quite an interesting paper coming from Google 2-3 years ago. Okay, so you can see that the performance of this method is really, really good on, and they evaluated on a lot of tasks. Yeah, so they evaluated it on a lot of tasks, and they showed consistent improvement across the tasks. Okay, for few shot. Some of them are outperforming the pre-trained, fine-tuned models for that specific task. Some of them will not outperform. Yeah, but that is fine, because this is for zero shot and few shot setting.